Okay. What is up? We are back with 2024 AMC 10A problem number 25. Okay, so we're trying to draw a closed loop on this grid. We're allowed to traverse along the dotted lines here. And what we need to satisfy is for each of these squares right here, like this square right here, exactly one of its four sides is part of this closed loop. So let's start off with a stupid example, which is just this path right here. This obviously works. This one obviously works too. All right, great. So I guess that gives us a final answer of 2. Unfortunately, 2 is not an answer choice. So that means there's some more non-trivial cases that we do have to consider here. So let's try working on this systematically right here. We're going to rigorously prove that we counted every single path that does work and we're not missing any. So this is going to take a while. Okay, so let's get started. So let's say we take this edge. It's just a random vertical edge in the middle. We're going to show that this is impossible. So let's say we did take this edge for the sake of contradiction. Then like at this point, we're on the closed loop, right? So we have to go one direction. If we turn left here, we're violating the condition on this square, right? Because 2 of its edges are shaded. Similarly, we can't turn right here. So we have to go straight up. Similarly, in this bottom part, we have to go down right here. All right. But now you may notice we have a problem. And that problem is, let's say we turn right here. So then we do some stuff here. Eventually, we have to come back to this spot, right? So we're going to have to come back from the right side. And now we finished our loop. And now the problem is these 2 squares don't have any edges on them. And so that's not okay. And that means that our initial assumption, we backtrack all the way right here. We cannot have shaded this edge in. So that is a problem. Okay, we can't traverse this edge. We also can't traverse this edge for the same reasons. This edge, and this edge. These are not okay to traverse. On the other hand, this edge is actually okay if you think about it, right? Because like if we take the same steps of reasoning before, like if we do like something over here, this is actually perfectly fine because this square is satisfied. And that was the issue that we had with those other edges, is that they kind of like split the board into half. Here, it's basically just the leftmost side already. I mean, this square is satisfied. This could work for all we know. And as we will see, it will work. Okay, so there's only 4 vertical edges left here, actually. That's pretty important. So we have these 4 vertical edges. Let's call them A, B, C, and D. So you might notice now our grid's kind of been like segregated into 2 halves. So we have that half on the top and the half on the bottom right here. And okay. So we're going to have to make an even number of crossings because we have to go like top, bottom. At some point we have to end up back where we started. And so we're going to have to make an even number of crossings, which means we can't like go this edge A, B, and D and not like do C at all because that's going to have an odd number of crossings. That's impossible. So we can either have 0, 2, or 4 crossings. 4 crossings, is that possible? Obviously not because we've already violated the 2 edge condition by just shading an A and B right here. Similarly, we can't shade in both C or D. So we have to pick at most 1. So that means that we either have 2 crossings. Let's see, I'm going to write this down. Okay, we either have 0 crossings or we have 2 crossings. Okay, so the 0 crossings case. This one means that we either pick the top half of the grid or the bottom half of the grid, and then we don't do anything. We just stay there the whole time. So what does that mean? That means we don't take any vertical edges this whole time. So how is every square going to have 1 edge shaded? That means it's always going to have to be, let's say, the top edge if we pick the top half of the grid. This is the only edge of these squares that we're ever going to get to touch. And so, yeah, these are all going to have to be shaded in. And now we can see our path is forced. It's just going to look like this. And so this was like the trivial case that we talked about at the start. And then there's another variant of this, of course, which is the bottom half. So 0 crossings, we've rigorously deduced that there's only 2 cases that occur from this. So let's pick a different color. Let's do black. There are times 2 cases right here. Okay, two crossings. Let's see. As we said before, you can't cross both A and B. You can't cross both C or D. So you have to pick either one of A and B and one of C and D. So pick one times from A, B. Okay, let's just write out the cases. So you can either pick edge A to traverse and edge C to traverse, edge B to traverse, and edge D to traverse. That's a tongue twister. You can also do AD, and you can do BC. These are our four cases. We pick one of the two choices from the left side, one of the two choices from the right side. And once we pick these edges, we have to count the number of ways to do the rest of the grid. Okay, let's start off with AC. Let's say we draw in edge A, draw an edge C, and we're excluding edges B and D. So what's going to happen now? Once again, for the same reason that we mentioned at the start, with these vertical edges, you always have to go straight up. Like at the top part of A, if we turn right here, we're violating this squares 1. So we have to go up here, we have to go down here, let's go up here, we have to go down here. Now what? Well, on the left side, at least for A, our hand is forced. We have to turn right here. There's a corner. There's no other choice. And for C, similarly, we definitely don't want to be turning right here because remember, our closed loop has to be like not self-intersecting. We can't like come back later. We have to commit to turning left right here. We have to turn left right here as well. All right, this is where the fun begins now. We actually do have quite a few choices. So let's analyze each square individually. So this square, we know we're not going to be taking any of its vertical edges. We're not taking this B, and we're not taking this edge over here either. Which means we either have to choose this edge or this edge. And similarly, for the next square, we have a choice between these two edges, and we have a choice between these two edges, and so on and so forth. And now the question is, once we pick an assignment of top edge or bottom edge for each of these, 1, 2, 3, 4, 5. For these 5 unit squares, once we pick a bottom edge or a top edge for each of them, how many paths are we going to have that correspond to those bottom and top edges? And the interesting thing is the answer is exactly 1 for every single assignment. So let's work out an example here. Let's say we pick like top, bottom, bottom, top. Should we do bottom or top here? Bottom. That feels very random. Okay. So what can we deduce from here? Well, first of all, is a path possible? Yes. Let's draw it out right here. So you'll see this is very intuitive. We just either stick to the bottom or top here. And we like don't want to go top here because now this square is violated, right? So we have to go down here. And so yeah, basically for that exact reason, our hand is completely forced here. Once we pick the top and bottom edge, we have exactly one way to continue it, which is you first draw on the horizontal edges, because now we know every single one of those. For example, these horizontal edges here, we know they're forced. They're not going to be down here, so they have to be up here. And then we just fill in the vertical edges as necessary. So that's cool. We can see for each of these 5 unit squares, once we made our bottom or top decision, everything else got determined. And that means in the AC case, there's just 2 times 2 times 2 times 2 times 2 ways to pick our bottom top edges, and hence that many ways to pick our path. So that's 2 to the 5 cases for AC. All right. What about BD now? Is that a whole new problem? Of course not. That's just this thing shifted 1 to the right. After all, our whole grid is symmetrical, right? So BD is also going to be 2 to the 5. What about AD? Well, the good thing is this exact same reasoning still holds, which is, I'm not going to erase the whole thing, but I'm sure you can imagine. Once again, now we have 6 unit squares in the middle, but the same reasoning holds for each of those 6 squares. We pick top or bottom, top or bottom, top or bottom. And so this one's going to have 2 to the 6 possibilities, because now there's 6 unit squares in the middle, like 1, 2, 3, 4, 5, 6. These would be the 6 unit squares in the middle. All right, and last case, BC. In this case, there's actually 4 unit squares in the middle, which are these 4, right? 1, 2, 3, 4. All right, so these are our 4 cases, plus this little case up here. I guess we have 5 cases. And now we just have to add it up. So let's do that. We have 2 plus 2 to the 4 plus 2 to the 5 plus 2 to the 5 plus 2 to the 6. And that's equal to 2 plus 16, that's 18. 18 plus 32 plus 32 plus 64. 18 plus 128, that is 146. All right. Thank you for watching. Please subscribe.